It's my great pleasure to welcome all of you to today's online seminar on interval methods in control engineering. And it's my great pleasure to have with us today Héctor Ríos, who is from the Instituto Tecnológico de la Laguna in Mexico. And he's a well-known researcher, having plenty of international collaborations, especially with Leonid Friedman, Denis Efimov, and several other colleagues, especially also Andy Thiel. And he's very much interested in the design of observers for linear and nonlinear systems, hybrid systems, fault diagnosis, sliding mode control, and also uncertain systems. And during his presentation today, Héctor will talk about an interval predictor-based robust controller for the blood glucose regulation problem. And Héctor, we're looking forward to your presentation. The floor is yours.
Thank you, Professor. Thank you for the introduction. I would like to say that I'm also working with Tarek. So he is also my friend and my collaborator. Okay, so as Professor said, today I'm going to present this solution for the blood glucose regulation problem. This is a work that was already presented in the last CDC, and it was a work done by me and a couple of Mexican friends, Manuel Mera and Alejandra Ferreira de Loza. Okay, so the outline of the presentation is like this. I will try to motivate the problem. It will not be very difficult because the diabetes is a very important health problem around the world. I will then try to introduce the problem statement formally, the solution, some simulation results, and some final remarks. Okay, so if we are talking about the regulation, the blood glucose regulation problem, we are talking about the diabetes. Okay, so the diabetes mellitus is a very important, very difficult health condition, which is chronic and incurable. It produces high blood glucose levels provoked by insulin lack, which corresponds to type 1 diabetes, insulin resistance, which is type 2. It causes severe damage to the body and increase the risk of premature death. Of course, there are only few complications, and there are more, like heart attacks, kidney failure, amputations. So it is a very difficult health condition. Some numbers about this health condition, numbers around the world. So in the 2021, there were around 500 million of people with this illness, and the projection is that in the 45 there will be more than 700 million of people with diabetes, with some type of diabetes mellitus. So in the world, 1 person in 10 has this problem. And in Mexico is worse, 1 person in 6. So it's a very important, it's a very difficult health issue, and is rising. Every year is rising. What else? When it occurs, when the type 1, specifically diabetes mellitus occurs, it occurs when the pancreas stops producing the insulin hormone. That's the issue. When the patient has this type of diabetes, just is because the pancreas stopped producing the insulin. The body is not able to regulate the glucose level. The type 1 diabetes affects 10% of the total diabetes mellitus patients. It cannot be prevented and may affect people of any age. The type 1 diabetes doesn't care about the age. The patients need daily insulin injection for the rest of their lives. And of course, there exist several factors which impact the blood glucose levels. For example, the food intake, the stress, some other illness, hydration, exercise, etc. And the insulin doses must match the patient needs. So for each patient, the doses could change. Okay, so what are the challenges in the treatment of this kind of diabetes? There are mainly two challenges. One is to keep the glucose level within the normal glycemia range most of the time, avoiding excursions to hyperglycemia, I mean high levels of blood glucose, and hypoglycemia, low levels of blood glucose. So for both of them, there are some issues. When you have some excursion into the hyperglycemia zone, there could be some chronic complications, coma, even the death. In the hypoglycemia zone, there could be also most of the people say that it's more dangerous, this hypoglycemia zone, because it causes also the death and some faints. So the issue is to try to avoid these zones and keep the glucose within the normal glycemia range. Okay, so the problem statement. Formally, we are using this minimal model, which was introduced by Bergman. And this model is composed by three differential equations. X1 is the plasma blood glucose concentration. X2 is the insulin effect on the net glucose disappearance. X3 is the plasma insulin concentration. U is the control signal, and it corresponds to the insulin infusion rate. We are going to design this signal to deal with this problem. In this case, D, the term D is the glucose absorption rate, and need corresponds to the disturbance. The food intake is a disturbance in this insulin glucose dynamics. IB, GB, P2, P3, and N are some parameters of the system. Okay. Some remarks about this insulin glucose dynamics. Of course, it has patient variability. The parameters depend on the patient. Okay, they change according to each patient. The food intake or the disturbance normally is modeled as a vanishing disturbance. It's modeled as this kind of exponential function, and it's just a vanishing perturbation. So it means that you eat, the blood glucose level increase, and then this effect is just vanishing along the time. And one of the problems of this insulin glucose, well, it's not a problem, but by nature, the glucose insulin model is a positive system. The state represents the substance concentrations, so they should be always positive. And of course, the insulin infusion is also positive. It can only take positive values. We cannot extract insulin from the body. So it is by nature a positive system, and the control signal should be also positive. Okay, so the control goal is to design the control signal U to keep the glucose within the normal glycemic band despite the food intake, the disturbances, and the unknown parameters, while keeping the following constraints. We want of course, the glucose level in the normal glycemia band, so it should be kind of constrained task. Okay, and also we need to consider that the control input should be positive, and there will be a maximum value for this infusion rate. So we have a regulation program for a constrained state and input constrained system. Okay, so that's the problem. So some antecedents taking into account that we are dealing with a constrained control program. In fact, there are only few results in the literature for this particular system, and some of them are based on MPC and positive invariant sets. You can find this paper. The issue with this paper is that most of them are patient-oriented schemes. So you should try to design the control for each of the patients, and that could be an issue. So also most of them need knowledge about the food. They need food announcement. Some of the variables are left unconstrained. I mean, the total constrained system is not taken into account for some of these approaches. When they use, of course, MPC, there could be some computational burden. You need more resources to design this kind of controllers. And most of them rely on full state measurements. I forgot to say it, but in this case, the only variable you can measure is X1, is the blood glucose level that you can measure. The other variables are, in fact, for this model, X2 and X3, they are like virtual variables. They are not strictly related. They are not like physical variables in the body. They are some like a virtual variable for this particular Bergman model. So the only thing you can measure is X1. And some of these, or most of this approach require the knowledge of the full state. Okay, so what is the contribution of this work? We are proposing an interval-based controller which consider only the output information. We don't need to compute the full state. Only with the output information we are able to design this controller. It respects the positive nature of the glucose insulin system and preserves the state and inputs constraints within the desired intervals, and it copes against the patient variability. We are going to see that this controller can be applied for how to say, for a group or of patients. It's not individualized, let's say. And also, this approach deals with unannounced food intake. So we don't need to know when the patient eats. Okay, and prevents hypoglycemia, because we are going to introduce a switching mechanism. You will see that these mechanisms prevents the hypoglycemia problem. Okay, so as I told you, this paper or this proposal was already presented during the last CDC, and we are still working in the, how to say, in the journal version. We are planning to apply this stuff to a real, let's say, real simulator, which is called Uva Padova. Okay, it's a kind of real simulator where you can prove your controllers to try to solve this regulation problem. Okay, so what is the methodology? The methodology is described in this diagram. The key issue is to establish an input and state constraints and rewrite the insulin glucose dynamics as an LPV-like system. Okay, so we are going to construct or to compute the regulation error dynamics, which will have a kind of LPV structure. And we are going to construct an interval predictor for this regulation error dynamics. We are going to provide lower and upper bounds for this for the solutions of this system. And based on this interval predictor, we are going to design a state feedback controller for the interval predictor. We will use then a kind of saturation function to deal with the input constraints, and then we will provide that control to the real system. So the main idea is to design an interval predictor for the regulation error dynamics, and then to control the interval predictor. Okay, that's the main idea. So, well, we introduced the regulation errors, E1, E2, and E3. So E1 is the regulation in the blood glucose level. So we have GD, which is a desired glucose level. For X2, it doesn't matter. It can take any value, any positive value. It doesn't matter which value. And in X3, we are going to introduce also a desired insulin basal value. Okay, so we can translate the constraints, the state constraints in these regulation error dynamics, which are described by these sets, E1, E2, and E3 capital. And Taking into account these regulation errors, the regulation error dynamics is given in this way. Okay, so it has more or less the same structure that the Bergman minimal model. It is a nonlinear system, which now doesn't need to be positive. Okay, the Bergman system is positive, but this error regulation dynamics doesn't need to be positive. Okay, but still it needs to deal with some state constraints. Okay, so this particular system doesn't have the properties we need to design an interval predictor. It means that it is not, if you take how to say, like a linear structure, the state matrix is not Messler, is not Hurwitz, so we need to do one step more. So to get the good properties of the system, we need to use like a backstepping stuff. We need to see the error E2 in the first dynamics as a virtual controller. And if we design this E2 as a state feedback of E1, we can write this another variable set 2 and deal with this kind of transformation. Okay, so now the new state of the system is E1. This set 2, which is given by E2 and the state feedback of E1. And if we are able to take this new state epsilon to 0, E1 will go to 0 also. E2, as zeta 2 goes to 0, E1 goes to 0, E2 will go to 0 also. And of course, E3 will go to 0. So we are like rewriting the problem now in this framework. Okay, if you see this regulation error dynamics, it has like an LPV-like form where this vector rho is given by the output and the parameters of the system, P2, P3, and N. And we have a new disturbance vector W, which is given by the food intake and some constant parameters, okay? So it's this P3 IDB. IDB is just the difference between ID, the desired basal level, and the real basal level of the patient, okay? So this is the new perturbation. Now the issue is to deal with this system. Okay, the matrices A and B, A, B, and F have this structure. Okay, so B is just a constant matrix, is the input distribution matrix. F depends on the output and some parameters of the system. And the same with A. It depends on the output X1 and some parameters of the system. Okay, so again, we can translate the state constraints and the input constraints into this regulation error dynamics. It can be written in this way. And in order to deal with these state constraints, we can use a kind of polytopic approach to then try to use some LMIs and check if the states belong to the constrained sets. Okay, so this is the issue now, how to design U such that we take the trajectories of epsilon to 0 or around a neighborhood of 0. Okay, so as I told you, the idea is to construct or to design an interval predictor for this particular regulation error dynamics. So the matrix A rho can be written as a polytopic 4 with this A0 constant matrix. This A0 constant matrix is given here. This matrix is now Metzler. It's a Metzler matrix, and in fact is Hurwitz. The parameters P2, P3, and M bar are some nominal values that we will fix. We have a cohort of patients, and we will take some nominal values of this group of patients. We will take these values. Okay, so the other matrices, the sum of lambda I of rho multiplied by the matrices AI are just the vertices of the polytope. And you can compute all these matrices taking the maximum and minimum values of all the parameters, okay? So based on one previous result given by Professor Denis Efimov, we can compute some lower and upper bounds of this sum of matrices. And the way is given here, okay? We can do the same for the sum of the matrices A, I, and the sum of the matrices F, Y. Okay, we can take more or less the same. We can compute upper and lower bounds for all these sums. And then based on this information, we can construct this interval predictor, which was also previously proposed by Professor Efimov. So according to the structure of the system, according to the properties of the matrix A0 and the way we compute the lower and upper bounds of these matrices, this is an interval predictor. So if we select properly the initial conditions, we will have some predictions of the regulation error dynamics, one upper bound and one lower bound. So the idea now is to design U such that this system converts to zero or to a region around zero. That's the idea. If we are able to design a controller to take the trajectories of this interval predictor to zero, that will imply that the real, let's say, real regulation error will go also to zero, okay? So how to design this controller? We are going to propose a switching mechanisms to prevent the hypoglycemia, okay? So if the value of the blood glucose level is greater than this value, the desired value, and the convergence region given by this matrix P, which will characterize an ellipsoid that we obtain later. We inject insulin. Okay, we inject insulin through a saturation function sigma. Okay, the saturation function sigma is given in this way. It's not symmetric because we need always a positive value for the insulin infusion rate. So we should take a minimum value, U mean, which should be positive, and the maximum value is just the constraint on the input signal. Okay, so we are using a not symmetric saturation function. When the insulin, when the glucose level is greater than this value, we inject insulin with this saturation function. And if we are close, or we are close to this region, we switch the control signal to zero. So we just stop injecting insulin. Okay, so that's the structure of the switching mechanism. Okay, so at the end, the state feedback controller, which is U bar, we will design U bar based on this state feedback controller. It's a nonlinear controller because we are taking the states of the interval predictor, and we are applying these operations. In this case, zeta plus, zeta minus is just taken as you can see here. know it's not given here, but it's just the maximum value and then the minimum value of the real vector theta. Okay, so we are going to design this state feedback controller U bar, and then we will pass through this saturation function, the same state feedback controller, to try to deal with the input constraints. So we need to design this matrix gains K0, K1, K2, and K3. Okay, that will be the problem now. So now we have the main result. The main result of this work is given in this theorem, and it basically says that if we are able to apply this state feedback controller with the saturation and some sets of LMIs are feasible, then the trajectories of the interval predictor will converge asymptotically to this ellipsoid epsilon, okay, which depends on this matrix, positive definite matrix P, and which is not centered in the origin. We have a convergence ellipsoid, but it's not centered in the origin. It's centered in this theta start, okay? So the trajectories of the interval predictor will converge to this ellipsoid, and then we are able to prove that X1 will converge to this region, GD plus the square root of the lambda max minus 1 of the matrix P multiplied by this constant asymptotically, okay? And at the same time, the rest of the states will satisfy the constraints as well as the control input. That's the main result. Okay? If we are able to find a solution of a set of LMIs, then the system will converge around a neighborhood of the desired values. So the set of LMIs, I'm not going to put all of the LMIs, but the set of LMIs are mainly related to all the constraints. For example, this couple of LMIs are related to the input constraints, okay? We take the minimum value for the control, the maximum value for the control, and we try to look for a solution, okay? Some of them also are related to the state feedback, how to find the matrix gains to ensure the stability of the regulation error dynamics. And these last elements are related to the state constraints. We get a solution, and then we see if this solution is inside of the, is inside the state constraints, okay? So the simulations results. We are using MATLAB for these simulations. This is the first step. Then we will try to go to the simulator, to the UVA-Padova simulator. But the first step is to try to do some simulation just in MATLAB using the minimal Bergman model. So we are taking a cohort of 4 virtual patients. Okay, they are adults and they have, of course, type 1 diabetes mellitus. The sampling time is 0.1 seconds. We are considering one single meal. It's, of course, a closed loop scenario. They have this single meal. They eat 80 grams of carbohydrates at the 5 hour, and we are taking 1 day. Okay, so the scenario is for 24 hours. Okay, and they have one single meal in this time. So the constrained sets are given here for the states, for the input. The initial conditions are given there. We take some minimal values, some desired values for the glucose level, for this insulin basal level. We take these desired values. The parameters of the patients, we are taking 4 patients, and these are the parameters P2, P3, IB, and N. These parameters are taken from the literature, from a paper of Bergman. So we take these parameters, and based on these parameters, we take the minimum and maximum values of all these parameters to construct the vertices of the matrices, and then construct the interval predictor and everything, and look for a feasible solution of the LMIs. Okay, so I didn't put the gains and everything, but for this particular system, we are able to find a feasible solution. We are able to find some gain matrices, and the results are these. Okay, so we have the blood glucose level for each of the patients, for each of the 4 patients, and you can see here we have the different zones. The white zone is the normoglycemia zone. So most of the time, the patients are in this zone, in the safety zone, let's say. There is a kind of peak in the hour 5, because at that time is when the patients have a food intake. At this time, they have this kind of disturbances, so the level of the blood glucose increase. But then the controller is able to take again the trajectories of this blood glucose to the normal glycemia zone. Okay, and you can see we avoid the hypoglycemia events, and also the hyperglycemia events. Okay, so the blood glucose levels are most of the times in the normal glycemia band. This is the control signal. This is the insulin infusion rate. And as you can see, most of the time the signal is just constant. Okay, when we are close to the desired value, the control simply turns off. Okay, that's the idea. I forgot to say, but this system has some particular properties. The insulin, the glucose insulin model is an stable system. Okay, by nature is stable. Okay, so you can take advantage of this kind of features to design the controller. That is why you can switch off the controller, and then by nature the trajectories of the system will converge to the desired value. Okay, these are the regulation errors. They are inside the constraints, and that's all. That's the results. So some final conclusions. We have proposed a blood glucose regulation control for type 1 diabetes mellitus patients. The approach somehow is robust against patient variability, because you can apply this controller for a complete cohort of patients, for a group of patients, and you don't need the announced food intake. Okay, the controller is able to deal with the food intake. The method considers, as I told you, the positive states and the input constraints based on this interval predictor. The closed loop analysis ensures the asymptotic convergence of the blood glucose level around the desired value. Somehow the synthesis is constructive, because it's in terms of LMI, so you can use a toolbox to get the control gains. The feasibility of the strategy is demonstrated in silico over a cohort of 4, in this case 4 virtual patients. And additionally, it is possible to apply the same kind of strategy based on the interval predictor approach to deal with some other problems. In fact, with Tarek, we have used a similar approach to deal with the trajectory tracking problem for state and input constrained mobile robots. Okay, so the same kind of approach based on this interval predictor stuff can be applied to deal with some other problems, considering state and input constraints. And that's all. Thank you.
Yeah, many thanks, Héctor, for your presentation. And yeah, who wants to start with the questions? Luc.
Yes, if possible. Thank you for the presentation. I have one question. I would like to know about your interval predictor. Do you have any
Yes.
idea of how far you are from the optimal one, the minimal one? Are you pessimistic, or do you have any idea if you are only a little pessimistic, or do you have any idea on this?
I'm a little pessimistic because in fact it's a very conservative. If you see, in fact, we are not using information of the system. We are just giving the, how to say, in fact, it is the worst prediction because we are taking minimum and maximum values and we are not using information of the system. So we are giving the worst possible prediction.
Yes, but if you, I understand. So, but how far you are from the worst prediction, which is feasible? You know, the worst prediction is a feasible one, but the upper bound you give is probably not feasible. It is. So, what is interesting is the distance between the upper bound you propose and the worst case. Do you understand what I mean?
Okay. Yes, we didn't, how to say, we didn't compute that.
No, but not compute, I understand, but do you have any idea of how far is of how big is the distance between the bound you compute and the worst case? Or you have no idea?
I mean, we didn't do it, but if we take into account the, how to say, for example, for this particular group of patients, if we take into account the values of the parameters, we can do it. We can have an idea of how far we are.
Yes, okay, but so you have no idea. Yeah, okay,
No,
I
at this
understand
point,
that.
no.
Okay. Thank you. Thank you.
You're welcome.
Yeah, maybe let me directly follow up this question, what Luc just has asked.
Yeah, I think that there is some pessimism due to the wrapping effect. If you put the equation, the dynamics of the predictor, there is the wrapping effect is clear here. But how to compute the worst case, I think that it's not easy. But I agree with you. There is some pessimism.
Yes,
Can I
because
ask?
as I said, we are in fact taking the worst case.
Can I ask some very simple questions?
Sure, Tarek, please go ahead.
Yeah. First, many thanks for this nice presentation, Héctor.
You're welcome.
My first question is about the sampling time. Is it regular or no? What about the sampling time?
In this case,
For the measurements.
for this simulation is 0.1 seconds, and this system is very slow.
Yeah. Do you think that it is for this value? Is it consistent with the simulator which will be used?
In fact, how to say? In fact, for the simulation, when we use the UA Padova simulator, which is a high fidelity simulator, in fact, the sampling time is bigger. It's around 10 seconds or something like that.
And for the measurements, are they regular in time or no? Or the idea, maybe I think that some techniques based on event triggered or time triggered techniques may be well adapted for this problem, I think.
Yes, the measures can be regular, and in fact, for the simulator, you can take the same, how to say, the same sampling time. Let's say 10 seconds. But in this case, if you see, we are only using the, where is it? It's here. As I said, we are not using really the information of the system. We are just like monitoring. If you see, if you are able to see the glucose level, if the level is in a good zone, just keep the controller keeps working. If you see that the glucose level start to decreasing, just stop. But we are not using, in fact, we are just like using the information, but just monitoring the glucose, the blood glucose level.
Yeah.
So you can take your time because this system is very slow.
Yes. So for MPC, is it the main motivation? Is it about to satisfy the constraints? What's the main motivation for using MPC for this application?
In this case, I'm not using MPC.
I thought that for control there is MPC also. Oh, okay. So okay.
No, it's just a state feedback controller based on the interval predictor. In this case, we are not using MPC.
Yeah, I thought that. Yeah. Okay. So maybe you can use MPC, yes, of course. So don't show these to satisfy the.
Yes, I mean, we can try. In fact, as I said, there are only few results, in fact, in the literature. You can find only few results which take into account the constraints of this particular system. You can find a lot of papers with control design, but without taking into account the state constraints, not the positivity of the control. And only few where you find these considerations, and most of them are based on MPC.
Okay. Thank you, Héctor.
You're welcome.
Yeah, maybe let's come back to the question that Luc had asked before concerning the pessimism. Do you think it would be possible to embed something like an online estimator that allows you to identify the patient's specific parameters, more or less at runtime?
I think that the first step is to use the information you can measure. As I said, in this case, we are not using even the output. We can try to update, let's say, the prediction using the output. For example, this is the first step to try to improve the prediction.
Yeah. Yeah, that means to extend your prediction in such a way that you have more or less something like an interval observer at the end.
Yes, exactly, like an interval observer instead of an interval predictor.
Yeah, and concerning the prediction, this pure predictor that you have is, I think this slide is perfect to discuss it, because you see there exists some pessimism due to the fact, like Tarek said before, this wrapping phenomenon. And could you reduce the wrapping phenomenon, for example, by, let's say, computing directly on sets, for example, propagating sonotopes or ellipsoids? Instead of determining the framers.
Yeah, I'm not sure. Maybe.
Okay, that means that will be something for follow-up activity to make this comparison.
Yes, I agree.
Yeah, and yeah, I understood during the previous discussion that the sampling time is not really critical for the high fidelity simulator that you want to take into consideration. But if you want to deploy the approach to a real patient, is there anything that could be critical when assuming the small sampling step size, although the system is that slow? Would it there be reasonable to do something like an event-triggered procedure?
I think yes, it could be a good idea. It could be feasible because it will take into account these kind of, how to say, sampling time. It's like kind of additional constraints related to sampling time. So in that case, yes, I agree. You can use some kind of event-triggered stuff. But in fact, according to the people who works in the simulator, this is I don't know if you have heard about this Uva Padova simulator, but it's supposed to be a high fidelity simulator approved by one American federation. I don't remember, FDA Federation or something like that. And according to them, if your controller works in the simulator, it is possible to apply it. Because the simulator, of course, it's not this, they don't use this simple model. They use, in fact, a model with more than 12 equations, different stuff. They take into account the dynamics of the pump and all of the stuff. And you can see there all these issues with the sampling time.
Yeah, and the final question that I have is you described very nicely at the beginning of your talk that diabetes is a really safety critical disease for human beings. You can die from it, in fact. And
yes,
the question is if your controller doesn't work as desired, if you have some fault, for example, in the control itself, or some malfunctioning of the pump.
Yes.
Do you know about any activities at the moment that are trying to combine such control procedures like you described with a fault tolerance strategy, fault detection and isolation approach?
No, to be honest, I haven't taken a look, particular in this fault tolerance control for this problem, but I haven't seen many works on this. Maybe I'm not right. Maybe there are, but I haven't taken a look. But yes, of course, I mean, you should consider in some point some faults, some actuator faults in this case.
Yep. Yeah, to get something like an early warning for the patient, maybe now it's better to call the ambulance or whatever.
Yes.
Yeah.
Yeah, in fact, I don't know if you saw, but there was a kind of book in the Control System Society related to the roadmap for control systems. And how to say, the roadmap says that safe critical systems, healthcare, is the future of control systems. So in fact, this glucose regulation problem is in the roadmap.
Yeah, it is obviously one of the important human cyber-physical systems to be considered in the future.
Yeah.
Okay, let me have a look again at the list of participants. Is there anyone else who wants to ask a question? If not, and again, many thanks, Héctor, for your presentation and also for the inspiring discussion at the end. And yeah, we're now coming to the end of today's seminar. We'll meet each other again on Friday in 2 weeks for the next online presentation. Thanks again and have a nice weekend.
Thank you. Thank you so much for the invitation.
Bye-bye.
Thank you very much. Bye-bye.
Bye.